All right, thank you. Welcome to the second session on language and systems, and our next speaker will be Adam Scibior, who will be giving us a semantic treatment of approximate Bayesian inference.
Thank you. So in the first talk of the previous session, Jean said that some students should start working on proving correctness of inference algorithms for probabilistic programs using some sort of formal semantics, and I'm happy to say that I am precisely such a student. Furthermore, you don't have to wait 60 years or even 6 years. The work is done, it is published, it's ready to be used right away. So I'm going to tell you all about it. And as Jean predicted correctly, the technical details are rather involved, so I'm not going to bore you with any of that. I'm going to just give you a very high-level overview of how things work and highlight some of the practical advantages we can obtain with this semantic approach. All right, so let's start with a short introduction to formal semantics, since I imagine many of you will have zero experience with that. This is my own understanding of what it means to do semantics and what it's for. Many people can disagree with that, but that's okay. They don't have microphones, so they shouldn't disturb us. Okay, so if you want to do formal semantics, first of all, you need to have a formal language. So you start by defining some sort of syntax, usually as a context-free grammar. I'm sure you all know how context-free grammars work, so we're not going to spend any time on that. And that tells you what kind of programs are allowed within your language. But then often this is not good enough, because some programs are nonsensical, such as adding a number to a function. And so you design some sort of type system that tries to exclude certain nonsensical programs and only leave the ones that actually make sense and do what you want to do. So in order to define that, you define some sort of grammar over types. And then there is a bunch of typing rules, as you can see on the bottom. So these are inductive rules that say a certain term has a type if the subterms have certain times, blah, blah, blah. And you can use all that to do nice proofs and whatnot. So this is the language definition. And then why do you even want to have formal semantics for it? I guess there are many answers to that question, and different people will have different views. For me personally, the most important thing is that having formal semantics allows you to reason about your programs more carefully, so you can better understand what it is that they actually mean and have a good notion of what it is that you're expressing when you're writing programs. But on top of that, it's also possible to use formal semantics to formally prove that your programs are correct, that they're doing what they're meant to be doing. And it also helps to implement compilers and design languages, select the features and whatnot. And there are three main approaches to doing formal semantics of programming languages. At least that's what the textbooks say. So there is the operational approach, which basically tries to simulate how the execution of a program occurs by reducing terms to other terms and so on. There is the denotational approach, where you associate programs and terms with certain mathematical objects. And then there is the axiomatic approach, where you establish what sort of effect your programs have on the conditions that hold before and after the program is executed. So in this talk, we're going to focus solely on the denotational semantics. And the way this usually is set up is that you define some kind of notion of spaces to which your types correspond to. Okay, so the formal semantics, the denotational semantics are usually written using those funny double brackets. So whenever you see anything like that in programming languages talks, you can expect there is some sort of denotational semantics involved. And the important part here, as you're reading this, is that there are two different languages. There is the formal language that you're giving semantics to, and then there is the informal mathematical notation that's actually used to express the semantics. And it's quite important not to get confused which is which. So here, the stuff that's inside the brackets is the formal language. On the right-hand side, there will be the informal mathematical notation. Okay, so if you want to define denotational semantics, you have a bunch of rules like these that tell you what types correspond to what spaces. So for example, a product type corresponds to a Cartesian product, and the function space corresponds to the exponential, which is just a weird notation for a function space. Okay, and once you have that, then you associate terms or programs with element of these spaces. Okay, so a term has a type, and these types tell you which space the relevant object will be in. And then you have semantics that tell you precisely what the objects it corresponds to. And usually when you do denotational semantics, you want to have a compositional property so that the denotation of a term only depends on the denotation of its subterms, as you can see from the rules here. All right, so that's like a very brief overview of how things work. And how does it work with probabilistic programs? So for probabilistic programs, types need to correspond to some other spaces than in what you're used to with normal semantics. In particular, the most sensible choice is to select some kind of measure space. So if we have a program of type alpha, so for example, alpha can be real, we have a program that returns a real number, then its denotation will be a measure over the space of real numbers. And the reason I say measure and not a probability distribution is because we potentially allow those things to be unnormalized. And that's quite important. You need to do that if you want to retain the compositional property. So whenever you introduce observations, you're gonna change the total measure, so it's no longer gonna be a normalized probability distributions. Okay, so it is possible to give the semantics to probabilistic programs in this way. So you associate types with measurable spaces, and then programs represent actual measures. So the big technical difficulty that many people struggled with over the years is that if you're trying to do that for a higher order language, so a language with higher order functions, then it is very problematic to define a measurable space for the function spaces such that everything works out correctly. In a sense, this is a somewhat artificial problem in that you can't really express the mathematical objects that cause problems as programs, but still, if you want a correct constructions, you need somehow to deal with that. So that's the big technical difficulty that Jean alluded to in his talk. So at this point, I'd like to give a shout out to Sam Staton and colleagues who developed the category of quasi-Borel spaces, which is a brilliant invention that allows you to circumvent all those problems and actually define denotational semantics for a higher order language. So this is precisely the technology that we have used to give the measure semantics, but of course that's only the beginning of the story, because I can say my program corresponds to a measure. It's good for reasoning about programs, but as we know, we can't really compute those measures because the inference is intractable. So in fact, what I execute is a sampler. There is some sort of approximate algorithm, and I'd like to be able to reason about that. So what we can do alternatively is define another denotational semantics, but this time programs do not correspond to measures, programs correspond to samplers. So on the slide, you see in a somewhat obscure notation, all it's saying is now programs correspond to samplers that take a random number generator and produce a value and a weight. So it's very easy to define an interpreter for a probabilistic programming language this way. So you just, every time you sample, you call a random number generator. Every time you observe, you just update some weight. And at the end, you spit out a sample and a weight. It's like a very simple importance sampling from the prior. So you can do that. It's easy in implementation, and it's easy to give semantics that correspond to this algorithm. But unfortunately, this is not very efficient. So this is not what we usually run in practice. So in practice, we want things like MCMC or SMC and variational inference and whatnot. So how can we develop semantics that correspond to such algorithms? OK, so that was the easy part. Now things get quite complicated. This is roughly the structure of the setup we're using. So we start with a model. The model is just the program code that specifies the probabilistic model. And what we want to do is to obtain a sampler. So this is like a normal executable code that actually runs the inference algorithms you're interested in. And the way we structure this, so in all probabilistic programming systems of this kind, there is some sort of backend that takes the model code and it produces the actual sampler. And the way we set it up is that instead of going directly from the model to the sampler, we're gonna do a sequence of transformations through intermediate representations. So these are completely deterministic transformations. They look a lot like normal compiler passes in a traditional compiler. And the crucial part is that each of these transformations will preserve the semantics. So each of the intermediate representations has semantics that corresponds to, again, measures. So we had the measure semantics for the model, and each of these intermediate steps, it also has semantics to correspond to the same measure, so that finally when you arrive at the sampler, it also has semantics that correspond to the measure by taking the appropriate, basically by integrating over all possible sources of randomness. So by setting up things this way, we can guarantee by construction that the sampler we obtain is correct. So how does it look like in practice? So say we want to implement the sequential Monte Carlo algorithm. So this, the block in the middle, the thing in the frame would in this case look like this. So the intermediate representations are composed of several layers, and these layers correspond to particular aspects of the program structure. So sum is just a simple sampler. It takes a random number generator and it performs sampling. Pop corresponds to population, so that you have multiple copies executing. And then sec is for sequential. So this is in fact a coroutine. So this stack it means that the program is represented as a population of coroutines. So this is precisely what we need for sequential Monte Carlo. And then in order to actually implement the algorithm, I do a bunch of transformations, start by spawning some particles, and then I proceed to interleave resampling with advancing the coroutines forward. And that this is, again, the operation of resampling is randomized, but in a sense, we implement it as a transformation that is deterministic. So all this random resampling is going to be put in this data structure, so that at the end, you have performed a bunch of deterministic transformations, and you have obtained a stack that consists of some pop, and that means just a sampler that spits out a population. All right, so you no longer have coroutines. At the end, you just have a sampler that's going to produce a bunch of weighted particles, and this is exactly what sequential Monte Carlo does. And the brilliant thing about it is that this is completely compositional in the vertical direction, so that if I want to do resample move sequential Monte Carlo, where I introduce a bunch of MCMC transitions after each resampling, I can keep pretty much the same setup, only now I introduce a tracing layer into the stack, so that's gonna keep a record of all the random choices made in the program so I can update them later, and then I'm gonna introduce this MH step in the middle of the transformations, but otherwise the whole thing remains the same. Okay, so that's basically how the semantics work. And if you're interested in any of the technical details, I'd like to refer you to our POPL paper. It was published earlier this year. This gives you all the details you could possibly want to know about it and more. Okay, so this is semantics. Now, what can we usefully do with it? So one thing is, so we have implemented a Haskell library that allows you to do probabilistic programming, and it implements inference algorithms closely following the semantic approach. So the library is available on GitHub. You can take a look, and there is an associated ICFP paper that was published just 2 weeks ago. Okay, so roughly just a highlight of the features, since we're running out of time, is this is a typical pseudocode for sequential Monte Carlo. This is pretty much what you would have to write if you were to implement this algorithm. And you can see that there is a lot of clutter here. There are some indices and whatnot. But in fact, conceptually, those are the things on the right that constitute the algorithm. So within our library, we can express this directly. So this is the actual implementation of SMC that you can obtain simply by composing several transformations. And dot in Haskell is just ordinary function composition. So you have your spawn at the beginning, you spawn n particles, and then you repeatedly resample and advance. And then there's just a little bit of extra glue that makes sure that things fit together nicely. Yeah, and similar for resample move sequential Monte Carlo. Pseudocode is even more complicated, but the implementation is still pretty simple. Just had to add a few extra terms. So that's one great advantage of this approach. You get this compositional structure that makes implementation easier and leaves you less room to make mistakes. But there is another feature that I'd like to highlight, and this is that it enables another way of testing your algorithms. So suppose I have a SMC implementation for my probabilistic programming system, and I'd like to test it. All right. It's pretty difficult to write a unit test for it, just because the algorithm is randomized, and it can give you arbitrarily bad results with non-zero probability. So I can never write a good unit test. If I wanted to have a high confidence in it, I would have to run it many, many times. It would be super slow. It's just not convenient to do. But if we have an approach like ours, where the sampling layer is independent of everything else, what I can do is take the sampling layer, remove it, and replace it with something that performs exact inference, for example, by enumeration. So then I can just stick it in, run my SMC on the toy model, exactly the same code, and then I can see that the exact enumeration results of the original model and after running SMC are the same. So that allows me to specify unit tests for my implementation. This doesn't catch all the bugs, but still, anecdotally, it's quite useful. Okay, so just a bit of what else may happen in the future. So what we have so far is implementations of basic samplers like MCMC and SMC. What we don't have so far is gradient-based inference, such as HMC or variational. On the semantic side, the problem is that the semantic framework for automatic differentiation is not very well developed yet. So that will have to happen before we can actually prove theorems about it. On the implementation side, this is probably doable today. It's just a matter of finding the right numerical library to make things efficient. Okay, then we can do potentially provably correct probabilistic programming systems. So what I have shown you here is that there is a calculus. For the calculus, you can prove that things are correct. And then there is a library that closely follows the calculus. So you can be fairly confident it's correct, but the correspondence is not exact. So there may well be bugs in there. But you can take it a step further and use formal verification techniques to really ensure that you've implemented the right thing. So that's on the cards, definitely. And finally, we'd like to see if this compositional approach enables any novel inference algorithms. So far, we have focused on re-implementing stuff from the literature, like particle MCMC or SMC square. But the obvious question is whether we can do something new with the building blocks we have. All right, thank you very much.
Questions?
Thank you for the talk. I did have one question, which was, this work is focused on formalizing probabilistic programming where you're not in the discrete setting. So you have real numbers and you need all the tools of measure theory. Now, on the actual computer, of course, we're not dealing with real numbers. So have you thought a little bit about what formalisms from maybe computable analysis or working with the computable reals that we'd need, maybe as a hybrid between these semantics, which are operating on fully real numbers, to maybe some limiting version of those, where you're actually considering that you're only in the space of computable real numbers?
Right. Thanks for the question. So I like to assume that the double precision floating point numbers that we have in a computer are real numbers, and I pretend that's the case. And I don't worry about anything beyond that. I think you could try to devise semantics in terms of computable reals. it would be even more hardcore than what we already have, and I think I'm not up to doing that. But if anyone wants to try, you have my blessing.
So actually just following up, did you have to do anything special about log space probabilities in your implementation? Repeat that.
So the question is whether we had to do anything special about log space probabilities in the question. So I assume you mean that we have log likelihood instead of likelihood?
Yeah, I mean, you talk about pretending that double are reals, and
Yes.
that made me think about very small reals.
Indeed. So yes, underflow is an issue here. And the way we deal with that in the implementation, we just have a separate numerical type that's called log double, and it represents things internally in log domain, but semantically it's a real number. So we get away with pretending that it's a real number and don't have to worry about underflow.
All right. Any other questions? If not, let's thank the speaker.